Hello, everyone. This is a brief update on the hybrid mu follower PCB, the revision 8, which, funny enough, it was made 5 years ago. And the purpose of today is to explain why I've done this. I have received several questions about this topic, which led me to find a way of explaining this very briefly. Although I usually have done it via email, I thought about writing a new PDF or an updated guide, but with lack of time, that's got postponed over and over. And I thought in the end it would be a good idea to record a video, which is something I've never done, but it's a format that a lot of people might prefer. And please do let me know if you like this, which might help in pushing me to record some other stuff. Okay. So, as an overview, we have what I'm covering very briefly in the next few minutes is what is the problem I was looking to tackle with this revision of the board. An additional benefit, which is the visual indication using an LED, which I'm going to explain in a minute. And I'm going to wrap it up with an example to explain and to walk you through how do we go about in calculating the different component values. So what was the problem, and what is the problem actually? Basically, when we are looking to design, to build or upgrade an existing stage using the hybrid mu follower board and changing the topology, we face a very common or very common amongst the builders, depending on the level of skill sets. We faced we make mistakes and we make incorrect connections, or we can end up with unexpected shorts in the circuit. If the stage or the amplifier would be only of formed by valves or tubes, as you call them, that'd be more prone to survive these issues. But with semiconductors or sand, as we call them, they are less forgiving devices, and in summary, they ended up dying straight away when you abuse them, and that death equals to a short, which of course is the end of the component, but it could also create further damage across the circuit. So obviously this is something we want to avoid. Right, so in this diagram on this, you would see a typical mu follower, kind of simplified, not so much on the board component side, but mostly on the surrounding elements that support the valve. I mean, there is no filament supply, there is no HT supply, there is no input or output connections. But fundamentally, if you haven't, if you don't know how this stage operates and how the mu follower works, I strongly suggest you look for the existing collateral in the blog. There is a very interesting presentation, which I may turn into a video, which is the presentation I gave at ETF on the year 2018. And I do cover the dynamics and the nature of this stage quite in depth. But for the sake of simplicity and the people who are not familiar with this circuit, I'm going to explain it very briefly. On this circuit, there is a constant current source, CCS, on the left, which is formed by the MOSFETs M1 and M2. That cascaded pair provides a constant current through the resistor R4, which generates a reference voltage. That current can be modified using the trim pot P1, and therefore you can define a range of the reference voltage to be set on. And that fundamentally what it does is it sets the operating voltage of the valve. It's not the current, just the voltage, the anode voltage. And in normal operation, everything is fine because the cascaded pair M3 and J4, actually J4 should be M4, but I think by diagram, the legacy denomination was a JFET before I had normally a MOSFET now in that place. But in normal operations, that cascaded pair will provide the sourcing current into the output stage load required, and will work in conjunction with the valve U1, sort of providing an impedance multiplying effect and a bootstrapping through the RMU resistor to make the whole stage, that totem pole, operate as a mu follower. I'm not going to go further than this, but obviously this stage is extremely linear, gets the best out of the valve for any given load, and especially when we're looking at to use it as a preamp or driving an output stage. Okay, so in normal operation, everything works okay. There is, providing you have the right protection in terms of heat dissipation for the different MOSFETs, the board has the right Zener diodes and protection diodes to make sure that nothing goes wrong during power on and switching of the amplifier. But as I said at the beginning, what happens when we have incorrect connections and or unexpected shorts? In the diagram, you'll see either a yellow arrow or the orange arrow as well, which shows the two paths by which excessive current can flow. Either we have a short or a defective valve, or we have some incorrect connection, or somehow a short at the output as well. It is not common, but it can happen. And believe me, throughout all these years and the hundreds of people that have built this circuit, I have found several people who unfortunately made the mistakes and they suffered because of this. So if you are not experienced enough and you cannot solder SMD, and even if you're not very good at desoldering, and we all hate desoldering, and it's not that easy to remove the MOSFETs, for example, in some cases, so without damaging the PCB. So if there is a short, and if you're lucky, you don't damage anything else in the amplifier other than the PCB itself and the MOSFETs. Who do you say goodbye? Generally, it's obviously the passing output MOSFETs, J4 and M3. Quite unlikely the CCS reference voltage will also go away. Not that common, but it can happen. So that makes the whole board useless, I would say. And in that case, it even make more sense to throw it away and start with a blank board, which is something we don't want to do. So, as I said, best case scenario, the silicon or the sand in the board dies. Worst case scenario, you produce some further damage throughout your ramp because you don't have the right protection on the HT, and there's a lot of current flowing through places it shouldn't go through. So as I'm saying here on the slide, now you know why I always keep saying and banging on user variac. It is very useful to detect situations like this when you're working. So the solution that I came about was to add one simple component was a resistor in series with M3 with a drain, and in parallel with the resistor is an LED, and I'll get back to the LED in a minute. So the resistor, what it does, it limits the current, and it's sort of like a fuse, if you want to call it, depending on how much current goes through, and if it's a low wattage device, it can blow away before the MOSFET, and maybe not. So there is no guarantee, but at least it won't be further damage, hopefully, across the circuit. And if you are worried about output impedance, forget about it. It doesn't add relevant additional resistance to the output, because that resistor R8, when it's transformed by the transconductance of the MOSFET, is kind of minimal. It's reduced to less than an ohm, so you wouldn't be worried about that. It doesn't. I have measured it. I have used it. I haven't even heard any impact of the addition of that resistor. Don't forget it's on the drain side, so that resistance gets divided by the transconductance when it's reflected to the source side. So it's in a position that doesn't affect. It doesn't also affect the stability of the stage unless that resistor is of a very big value. Generally the M3 is stable enough. We're talking about resistance of values of 100 to 200 ohms at the most, and that's not a problem for the MOSFET. Of course, if you add a very big resistance, then the challenge you have is that the power dissipation requirement is very big, unless we're driving a very low current triode, for example. But anyhow, in normal cases, somewhere between 100 to 200 ohms, that's what you're going to end up with. And I use carbon comp 1/8 or 1/4 of watt value. That's what you should do. And yeah, the second component is the LED, and you're not required to install it. Most of the cases, you can omit it. Nobody wants to have a visual indication, but if you do, you can add an LED and have some visual indication of the normal operation of the board. On the left side, you can see the through-hole version of the board, which you can see where the R8 and D4 are located. And on the right-hand side on the diagram, you can see the addition of the two components in the circuit. So how do we calculate and how do we use this resistor and this diode? If we don't want any visual indication, we just simply fit the resistor R8, and as a current limiter, you don't need to put the LED. That's one scenario, and it's quite common. In my cases, if you're gonna have the board inside a chassis and you're not bothered about any visual indication, just don't put the LED and you're fine. The second scenario is you want some visual indication. You can either expect to have some constant operation of the LED, or just to indicate whether the board is operating and there is some current throughout the anode, which is very useful. And the second option is whether you want the visualization to happen when there is a specific scenario where the current goes through a threshold. That's for example, if you have the board part of a driver that it's managing a transmitting valve in A2 operation. So when there is the amplifier is being pushed into A2 mode, then there is going to be current flowing from the hybrid mu follower into the grid of the output valve, and you want to visualize this, and this is something you can do as well. So how do you calculate the values of the components? Very simply, on the right you will see the equations, straightforward. You know the LED only turns on once the voltage across the device exceeds a threshold, typically 1.8 volts to 2.5 or 3, depending on the type of LED and the color, of course. But fundamentally, once it's on, it has a very low resistance. And the LED has a minimum current to emit, and you have, of course, a maximum current that will the device will sustain depending on the LED. But in summary, because if you remember those two devices, the resistor R8 and the LED are both in parallel, and that current flowing through the cascaded MOSFETs goes into the anode of the triode or the pentode valve. So that current through the anode is the sum of those two currents, the current through the resistor R8 and the current through the LED. So if we rearrange, you can derive that the resistor value would be voltage LED divided minus, the anode current minus the current through the LED. So that's basically how you do. You need to know what's your anode current, whether it's going to be the peak one or the constant one, for you want the LED to be turned on. The current that you want the LED to flow through the LED when it's on, and the forward voltage of the LED. Those are the values you need to know. So as an example, think about the 10Y or VT25 stage with a quiescent current of 20 milliamps. And I have a red LED to be used, so typically they have 1.8 to 2 volts forward voltage. And if you look at it, let's take 2 volts for example. You want at least to have 5 milliamps throughout the LED. LEDs can withstand 20 or 40, depending, some obviously more, but normally having 5 milliamps or even 10 at the most should be sufficient for the LED to be bright enough. So you put all the data into the equation I showed previously, and you can clearly see that it's you need a resistor of 130 ohms. Of course, if you use 120 or 150 ohms will work anyway. The more resistance you put, the higher the resistance, the more current will flow through the LED. You need to be careful with that. and the lower resistance value you put, you risk the risk of that there is not enough voltage across the R8 developed to turn on the LED, and therefore the LED will not turn on. So, right, so this is it. I hope you like this video. Yeah, it's a 20 odd minutes. I thought it was going to be shorter, but I hope I have covered everything required around this topic. And if you have a question about this or anything else, you know where to find me. Thank you.